Hi there, welcome along to a little video that is going to showcase a little problem-solving task I gave my sixth formers today to do with plate tectonics. We've been taking a look at all sorts of different types of plate margins. So I gave them this little transect across the southern part of the Pacific Ocean, going from the Tonga Trench through the East Pacific Rise down here to the trench at South America. This was the little cross section, and the first question that I asked them was to draw a simple diagram of which direction the subducting slab is going to be heading down at both A and B. Now, they've covered enough detail on the processes that make the plates move that they should have been able to figure this out. Of course, at a subduction zone, the subduction process is asymmetrical. The slab goes down one way or the other. So they did very well with that. They figured out pretty quickly that if you've got the ridge in the centre, you're going to be getting the slab pull here at A, slab pull here at B, ridge push in the centre. So they drew something like this. I just checked it out with them up at the front on the flip chart. But then we came to an interesting question. I was hoping they would get that right. This is the one. Draw the full cross section from A to B, all the way through here, through the ridge, back to the trench over here. This was an observational task because what I wanted to see if they would notice that the ridge is not right in the middle. This is a little bit off-centre, it's asymmetrical. So I got them to draw this down. It's a really good way just to get them to sketch this out, and they can externalize what they're thinking, and I can see and check for understanding pretty quickly. And this is roughly what they drew. They were able to observe. I told them this is an observation task. They were able to observe that the ridge wasn't quite in the center, and that was the simple diagram that they did. Going from the plan view there, this was the cross-section view. But here came the next question. If the ridge is further to the subduction zone in the east, it's closer to this one than over here, then which slab is subducting at a steeper angle and why? We've moved from simple observation and problem solving to connected problem solving because they had to bring together quite a lot of information from their prior knowledge in order to use this to solve it. And I was delighted when they all got the right answer. I wonder, can you figure it out? Now, of course, there's getting the right answer, but is there getting the right answer for the right reason? So when I went and had a conversation with them, this was the reasoning. This ridge is where the new plate material is being created. If it's created here, it's new and it's young. The further away it moves, the older, the colder, and indeed the denser it gets, and the more it sinks down. So because this has had a chance to move further, it's colder, sorry with the dog, colder, older, and denser, therefore it's going to subduct at a steeper angle. Brilliant. The right answer for the right reason. And that brought us to a hypothesis. The slab at the western end over here is subducting at a steeper angle because it's colder, older, and denser. Now the question is, could they find some corroborating evidence for that? And for that, we went into this GIS app that we've been using, TectoGlobe 3D, which is brilliant for this. So we said, what kind of evidence might help corroborate this? Because they've been using this for a while, they know that some of the information that is available for them here includes this kind of thing here. And we can come here and turn on the seafloor age, because that would absolutely corroborate it. And look, lo and behold, let's zoom in to this area here, where the subduction over at this stage, a mere 40 to 50 million years old, middle age at best. We come all the way over here, and it's getting older, older, older. And at the trench here, we're 80 to 100 or 100 to 120 million years old. Older, colder, denser, and therefore would sink in more quickly. And that's exactly the kind of corroboration that we were looking for. That's the pupils having a little bit of an explore, and this is me starting to collate this together at the front of the room. This is the steeper subduction zone over here, the more gently subducting zone there. But Can we get more corroborating evidence? Yes, of course we can. Let's go back into Tectoglobe 3D, because there's another set of brilliant data that we can use, and that's the seismic tomography, the CT scan of the mantle. So I'm turning on this layer that's currently buried in underneath the globe, that's going to be enabling us to do a slice through and see what the slab looks like. So I need to come over for an action here. I'm going to draw my cross section. So let's come over here first of all to the area where it is not quite as old, cold and dense, and let's draw on our cross section, and it will appear over here. There is the subducting slab going down, initially at quite a gentle angle, and then it starts to dip in more steeply. We can corroborate that further by adding on our hypocenters. There are the earthquake hypocenters going down, confirming this indeed is the subducting slab. But what about over on the other side? Is it subducting down at a steeper angle? Let's draw this on and find out. And lo and behold, there it is, subducting at a much, much steeper angle than the other one that we've just looked at. And this is exactly, I'm just going to change the depth that slightly so we can see it a little bit better. There's the steeper angle of subduction just at this stage, which is exactly what we would expect to find. And it's this brilliant corroboration that we can get the students to do using these GIS tools. This is them in action again, doing this corroboration, looking at this subducting slab going down. So we were able to pull this all together and take a look at our different slabs going down at those different rates and angles because of the difference in the age and how cold and dense they are. But it gave me an opportunity then towards the end to just reflect with the students as to why that might be the case. If this is subducting here against another bit of oceanic lithosphere, then probably this is cold, old and dense enough to subduct all by itself. It's got to 80 to 100 or maybe even 100 to 120 million years old, and it's just cold, old and dense, and it wants a wee sit down. Whereas we come over here, a mere 40 years old, a youngster, I would say. But I would say that what we have here is a plate that maybe doesn't want to subduct just yet. So why is it subducting? Because it's meeting the more buoyant continental plates, continental lithosphere, which is too buoyant to subduct. And when the two of these meet, this is the one that does have to subduct down. So it's subducting at a much, much more gentle angle because it is not inherently, quote unquote, wanting to subduct just yet. So a little bit of application task, a little bit of problem solving, a little bit of scientific process in action with us coming up with a hypothesis and a little bit of using GIS to test that out. And it's just brilliant to see the pupils thrive when they're given opportunities for this really powerful learning like this.